This is a continuation of equations from Composition 1. And we're going to start with reactants. The left side of the equation, and the reactants are going to be hydrogen gas and nitrogen gas. Okay, now it's going to yield, that's the yield side, produce products, or in this case a product. The product is going to be ammonia. Now, on this arrow, the beginning equations usually in books don't list anything, but I'm going to try to tune you in very quickly to show you the significance of this arrow as part of the story. If you take hydrogen and nitrogen facts and put them in a container, nothing happens. You get no ammonia. None. No ammonia. If you vary the conditions, you start getting what's called a reversible reaction. You get something of both, and you have to go through a very complex process. Now, this equation is one of the simplest equations, yet it won the Nobel Prize. Now, why did it win a Nobel Prize when it's so simple? Because remember, the facts after the facts, and this is the first step, you get the facts of an equation, and the facts we gave you. Then the second thing you do, you write correct formulas. Don't cheat on this process. Make sure you look at the facts clearly. Then make sure you get all the formulas right. So what's the formula for hydrogen? If you say hydrogen is H, no, that's the symbol for hydrogen. Hydrogen is a diatomic gas. That means two atoms are joined together in every molecule, and it is a gas. If you write nitrogen as N, you are wrong. Nitrogen is one of the 7 diatomic gases. Now, the reversible process, we can write the arrows this way, yields a molecule that you'll be studying as you go along called ammonia, NH3. Now, why did this win a Nobel Prize? This is a simple thing. An elementary student could do this, well, middle school. So why? The answer is in the yield process. Fritz Haber, in the early 1900s in Germany, was faced with, in World War I, faced with trying to help his beloved Germany produce explosives and fertilizers to feed people. So he knew that these two gases would make ammonia, but he didn't know how to do it until he figured out, and he used something you'll learn later on. He used a catalyst, and this catalyst that we will put down here initially used some osmium, ruthenium, iron we'll put. He used a relatively low temperature, maybe 300 degrees Celsius, and extremely high pressure, 200 atmospheres or more. He couldn't do this on his own, so he worked with a famous industrialist by the name of Bosch. So let's get these two names down. Haber won a Nobel Prize, and Bosch won a Nobel Prize much later, in about 1930. Haber's was about 1918, I think. We have Bosch Industries in the United States now. So Haber and Bosch process makes ammonia. Remember, the first step is get the facts. Second step is formulas. Third step is balance the mass. Now, you balance the mass by balancing the atoms. Balance equation, and you use coefficients. So, even and odd numbers is a good way to start. When you see a 3 and a 2, you're even and odd, you know you're going to deal with that. 3 hydrogen on the right in ammonia, 2 on the left. So the common number between 3 and 2 is 6. How do we get 6? We put a 3 here. 3 times 2 is 6 moles of atoms. 2 times 3 is 6. And you have 2 nitrogen, and you have 2 nitrogen. Look at the coefficients. They're 3 and weak at this. This is 1 understood. We don't usually write 1. But you have 4 moles on the left, 2 on the right. The moles sometimes will balance out, but most often they will not balance out. The moles aren't the issue. The atoms are what must balance out. The same number of atoms on each side, and that's what you balance. When you have the atoms balanced, you have the mass balanced. Fritz Haber got in big trouble in World War I. He became the father of chemical warfare, really poisoning people on the front with chlorine canisters. His wife was a PhD chemist, and she was upset. She committed suicide. When Haber got into his World War II, then started to approach. He was forced out because he was Jewish. His son in World War II, as a matter of fact, didn't know this till not too recent, just a short time ago, that his son also committed suicide at the end of World War II. So Haber was a great mind that had a pretty sad life. Fritz Haber. Now, let's look at this equation. Equation number 2. If we take carbon, and see, I'm going to skip the facts, I'm going to just put it in, and hydrogen, gas, put them together, I could write this equation, CH4. 2 hydrogens here, 4 there, I could put a 2 there, and it's balanced. But guess what? This does not happen. If I would go to the facts, I couldn't get this. Carbon and hydrogen, there are thousands of compounds of carbon and hydrogen I could write here on the right side that would balance. This does not happen. So that the facts have to be important just because you can balance the equation. So let's balance one that is a pretty neat one. Sodium. Sodium metal reacts with chlorine gas. Chlorine is diatomic. Now here's a very dangerous metal that burns in the air. Here's a poisonous gas, and we put these together and we eat the product every day of these 2 things. Sodium chloride. 2 chlorine, and we have to put a 2 here to balance the sodiums, and we have the equation. So we played around with a basic composition. The next thing I would like you to do is look at, instead of composition, decomposition. And the next tape, decomposition equations. And we'll stop right there.